Hello everyone, and welcome back to another Eng 130 video tutorial. In this tutorial, we're going to cover the 2016 final question 4, which I've got a lot of questions about because it's a really mean Centroid question, but it's very good to know because these 3D ones are probably the most complex ones that you guys can find, so we're going to cover it, and hopefully it shouldn't be too bad. So just by looking at the shape of this, you guys are probably already a little bit scared, but don't worry, because the method for 3D Centroids and 3D moment of inertia, well actually, not 3D moment of inertia, because this one's actually not 3D, but the method for 3D Centroids is usually the exact same. So if you guys can understand this, you guys will understand 3D Centroids very well. So looking at this question, I'm just going to switch to the highlighter. It says, determine the centroid for shape A. And this is very important because a lot of you guys will try and determine the centroid for this whole kind of, well, it looks like a bullet, but it's not a bullet. But we only want to find the centroid of this shape right here. So we're ignoring shape B and we're just paying attention to this purple shape right here. So it's not too bad. So that's the only shape that we want as shown in figure 4. And then it says in terms of the radius, and it has the radius. Oops, we can switch back to this. It has a nice equation for the radius in terms of the base radius R as well as the height Z. So we're going to use that equation quite a bit. So we're going to start off this by just going down here. And we're going to say part A. And remember, for 3D moment of inertia, so I'm going to say moment of inertia lots, but we're actually talking about just centroids. For 3D centroids, we always have the same formula. So it's going to be in terms of what is our height. And if we look at this, we're going up the z-axis here. So what we're going to have is z bar is going to be equal to the integral of z squiggle. And since it's 3D, it has to be a dv. So the volume, because we're dealing with 3D, so usually we have dA, but that's for 2D because we only deal with area. So for 3D, we have dV for volume over the integral of dV. So just like this. So it's not too bad. As you guys can see, you guys can easily start solving this on your own. So coming down here, all we have to realize is, well, we only need two things to solve this. The first one is what is z squiggle? So this is equal to whatever. And then what is dV? So it's the same process as we did before, where we would take a slice of a 2D shape and determine, usually it's y squiggle or x squiggle, and then we would determine dA based on the slice. And it's the exact same thing we're going to do here in 3D. So looking at this shape, I'm going to take a slice. And what I'm going to do is I'm going to kind of cheat a bit, and I'm going to take my slice, where they have this little dotted part right here. And remember, the slice has a minuscule, like a very tiny, tiny height, like this. So I'm definitely not drawing this to scale, but oops, the height, there's going to be a little bit of height. So the slice right here we model as like a little cylinder. And one thing that's nice about 3D is for our squiggle, so if it's y squiggle, x squiggle, z squiggle, whatever it is, remember it's the distance from the axis. So in this case it's going to be the xy plane, so it's going to be the distance from this plane down here all the way up until the centroid of the shape, which is right here. So this is right here, this height, which you can't really draw too well in 3D, but this right here is our z squiggle. And for 3D shapes, I've only ever seen it where z squiggle is just going to be equal to the variable that we're searching for. So if we're searching for y squiggle, it would just be y. If we're searching for x squiggle, it would just be x. And I've never really seen a case where it hasn't been like this. So coming down here, and we have these unknowns, well, I'm going to erase the question mark because we know that z squiggle is just going to be equal to z. And for 3D, I've never seen it where it's not like that. It's always like that, which makes it really easy for us, really great. And now dV, well, that's going to be the volume of our little cylinder, our cylinder slice. So we know that the height of the cylinder is going to be dz, or dz, like this. And we know that the area of a circle is going to be pi r squared. So what I'm going to do is I'm going to erase this, because we know this is going to be the area of the circle times the height. So we got pi r squared multiplied by the height. But the height isn't just h, it's actually dz. So pi r squared dz. So just like this. So from here, what we can do is we can substitute everything into our integrals to figure out what we want to know. And what I'm going to do is I'm actually going to separate these into two integrals. I'm going to do the integral of the top and the integral of the bottom. And the reason why I'm doing this is because the integral of the bottom here, this dv, Well, that's the volume of the shape. And if we have to do anything later to the shape, such as a centroid or even moment of inertia, we're going to need that volume. So that's a good value to have all by itself instead of doing this as one integral. So I'm going to come down here. I'm going to say, okay, well, we have the integral of the top, which is the integral of z squiggle dv. Well, based on our slice, we figured out all this. So we know it's going to be the integral of just regular z, and then times pi r squared times dz. So looking at this integral, it's not too bad. We have z, which is perfect because we're integrating with dz. We got pi, but pi is a constant, so pi doesn't really matter in this case. But the only problem that we have is this r factor right here, this r squared, because r changes. So it's also another parameter, it's another variable. And we can't integrate r with respect to z. So we need to somehow take this r that's in this equation right here and modify it so that it's in terms of z. And the way that we do that is always with the equation they give us. So if we come up here, I'm going to do some purple, they actually give us a nice equation. Oops, I don't want purple highlighter, I want a purple pencil. They give us a nice equation for r that's in terms of z. So right here, I'm going to make a little note here that we know that r is equal to the square root of big R, and that r is fine because that's a constant. So if we have constants in our integral, perfectly fine. We just don't want variables. So we got that big R, and then r, and in brackets, r minus z over 2, and that's it. So what I can do is I can now take this equation and substitute it in for, oops, that line looked pretty ugly. We can substitute it in for r, and in the end, once we write down our equation, which I'll do right here, so after we do this, we'll have the integral of z, so the z at the front stays, and then we got pi, and now we have r squared, but we now know that r is equal to the square root of r, and then brackets, r minus z over 2, and then we'll end the square root. So this is what r is equal to. And we know that in our original equation, it's actually r squared. So we're going to square all this and then multiply it by dz. And this works out really nice because when we square r, it actually gets rid of the square root that we have inside. So simplifying this a bit more, what I'm going to do is I'm going to take the pi out because it's constant. I'm going to have the integral of z. But now, once I square the square root, it goes away. So we're just going to have r times r minus z over 2 multiplied by dz. So now things are starting to look a little bit better because, one, everything now is in terms of r, or big R, which is a constant, so that's perfectly fine, or z. And z is great because we're integrating with respect to dz, we're good to go. So I'm going to actually just rearrange this a little bit to make it a little bit nicer. And the first thing I'm going to do is I'm going to say I have an r right here. And this is a constant value, so I'm going to take that r out. Because anything constant we can just take right out of the integral. So doing that, I have the integral of, or my equation will be pi times r times the integral of zr minus z squared over 2. And you guys may be going, okay, hold up, Clayton, you went a little too fast. You're starting to get parameters I don't know. So let's just rewind and figure out what I did. So I took the r out, the first r out, which is how I got the r outside. And then I took the z here, and I multiplied it in to both the r, which is why I got zr, and then the z squared, z over 2, which gave me z squared over 2. So now I have this integral right here, and at this point it's ready to be solved. So one last thing that we're going to have to do is we're going to say, okay, well, our integral is good, it's ready to be solved, but we need to find our bounds. And if we come up to the axis, well, the shape starts at the origin. So we know that our bottom bound, and I'm going to put this in orange, we know that our bottom bound is going to be 0 because it starts right at the origin and goes up. But now the question becomes, what is the top bound? Or the top limit. So top limit, because if we look at this diagram right here, it doesn't give us a top limit. It doesn't say where this shape ends all the way up here. So now we have to figure out, okay, well, how do we find that? And we're actually going to have to go to our equation up here that has to do with the radius. Because if we look at this shape, the radius gets smaller and smaller and smaller, and then at the very top of the shape, the radius goes to 0. So r is equal to 0. So we come to our nice equation where it says r is equal to the square root of r, bracket, r minus z over 2. And I'll put the square root over it. And we know that we're going to the point at which r is equal to 0. So this must be equal to 0. Well, if I move the square root to the other side, the square root of 0 is going to be 0. And if I move, sorry, I'll kind of clarify this. And then once I move this r to the other side, well, r times 0, oh, that's going to be 0 as well. So what we end up getting is this. Coming down, oh, I guess I'll stay in orange. We'll get r minus z over 2 is equal to 0. So now I can solve for z, which is going to be my top limit, and I find that z is equal to 2 times r. So this right here, this is going to be my top limit. And usually they're going to be nicer and they'll give you the top limit, but if they don't, this is when you have to kind of realize, okay, well, I have an equation that describes the radius. And what happens to the radius as it approaches the top? Well, of course, we see that the radius goes to 0, so I can make that equation equal to 0, and then I can solve for the z value at which it goes to 0. So now I can substitute both these limits in, and I get my top integral, and I guess I should put the pi r out in front. So I get pi r, and then multiply it on the inside. We have zr minus z squared over 2, all integrated with respect to dz, and our limits are from 0 to 2r. So that's not too bad. We can go forward and we can solve all this. And when we do, what we get is this. We get pi r on the outside, because that doesn't change. And in brackets, once we solve the integral, we're going to get z squared times r, and then we have to divide it by 2. Oops, that's the worst divide by sign I've ever seen. So divided by 2, and then minus z cubed divided by, and it's going to be, we're going to have to put a 3 down there, which comes from the integration, but that 3 is going to be multiplied by the 2 that's already down there. So in the end, we're going to have divided by 6, just like this. We can end this bracket, and we know that our limits are from 0 to 2r. Well, when we sub 0 into both of these things, the z squared r or the z cubed, well, it's just going to be 0. So the only thing we have to worry about is substitution of the 2r. So when we come in here, we're going to get pi r, or pi times r, and then times by, and we're going to have to put the 2r in. So we're going to have 2r squared multiplied by r divided by 2, like this. And minus, and then we're going to have 2r here, but this time it's cubed, and this one's divided by, oops, that one went up a little too high, divided by 6. So not too bad, because now we can just simplify everything, rearrange it, and we're good to go. So just doing that real quick, might as well. We got pi r, and in the top, or in the first one here, well, 2 squared is going to be 4. And then r squared is going to be r squared. But then we multiply it by the r on the outside. We get 4r cubed. And this is divided by 2. Minus, and we got 2 cubed, which is 8. Minus r cubed, or sorry, r cubed, which is r cubed. And we divide all this by 6. So we can just kind of rearrange stuff like this, and in the end what we get is all this is equal to pi r to the 4 times 2/3. 2/3. So just like that, we get pi r to the 4 times 2/3. So I'm just going to put it kind of down here, maybe in a different color. That 1, which is what I usually like to call the top integral, is equal to 2/3 pi r to the 4. So I'm going to come up here and I'm just going to clarify what I mean by 1. I'm going to say that this integral here, or where to go, this integral here is equal to 1 divided by 2. So we figured out what 1 is, the top integral, and well, now we have to solve for the bottom integral, which is going to be really, really easy because it's easier than the first one. So the second integral is dv, just the integral dv. So we know that it's going to be the integral from 0 to 2 pi, the bounds do not change, times pi r squared dz. So everything stays the same. The only thing that changes is we don't have that extra z from the z squiggle out in front. So we can make this a little bit easier because we know our equation for r. We can actually just come back up here and we know that this is going to be equal to the integral from 0 to 2 pi. And we can actually take this pi out. So I'll take the pi out, and then we got r squared, which just comes from our equation up here. So it's going to be r bracket r minus z over 2, all multiplied by dz. And we can make this even easier on ourselves because we can take out that extra r. So we get, I'll go down here, we get pi r multiplied by the integral from 0 to 2r. And I put from 0 to 2 pi in these ones, I don't know why. These should be from 0 to 2r. And this is going to be r minus z over 2. All integrated with respect to dz. Excuse me. So I can come down here even further, and I can say, okay, I can integrate this and go, this is equal to pi r, and then in brackets, well, the integral of a constant r, well, it's going to be r times z, and we're going to minus z squared, and then we're going to divide by 2, but there's also a 2 down there, so it's going to be divided by 4. And then this is going to go from 0 to 2r. So again, we don't worry about the 0 because the 0 is not going to do anything. It's just going to make everything go to 0. So the only thing that we're going to actually worry about is the 2r. So we know that this is going to be equal to pi r multiplied by r. So r stays the same, but for z, we have 2r minus z squared, so 2r squared, divided by 4. Oops, that didn't work out. Divided by 4. And all we have to do now is just go in here and simplify everything. So we get pi r, and then we're going to have 2r squared minus, and then we have 4r squared divided by 4, so it's just going to be minus r squared. So once we simplify this even more, what we get is pi r multiplied by r squared. So therefore, and I'll do this in pink because this is 2 now, 2 is going to be equal to, and it's just going to be pi r cubed. And what's, oops, sorry, I dropped a piece of paper. So what is also nice is this is actually equal to the volume of the shape. And we're going to need that volume later on, so it's very important to have. So looking back, remember our integral at the very top here that we want for our z bar, it's just 1 divided by 2. So we go over here, we're going to go z bar, which we know is just 1 divided by 2. So those two integrals that we already solved. So we know that 1 is equal to 2 over 3 pi, and then I think it's r to the 4. Yep, r to the 4. And all this is going to be divided by the bottom one, which is pi r to the 3. So it's actually very nice to see. We can get out the red cancel marker and we can say, okay, well, the pi's are going to cancel. Sorry, the 4 on the top is going to cancel with r cubed. So our final answer here is going to be 2/3 of r. So this is our z bar. Now if we look up to the question, it doesn't just ask us for z bar, it wants the centroid. So it wants x bar, y bar, and z bar. But since this shape is symmetric, we can say that we can easily see that x bar is going to be equal to y bar, which is going to be 0. So down here, we can say that our centroid x bar, comma y bar, comma z bar is going to be equal to 0, 0, and then 2/3 of r. And since this is our final answer, we're going to put a nice box around it to show everybody that we're done. Perfect. So this was part A, and this is I did a lot of extra work. You guys can probably solve it a lot faster than I can, but it is pretty beefy part A. So hopefully it gets a little bit easier moving forward. And it kind of does, because it says given the density of shape A is rho, so it's just parameter rho, and the density of cylinder B is 2 rho. So we can see from our diagram that B is actually kind of down here, like this. So we now know that that's 2 rho. It says, what are the coordinates of the center of mass? So I'm going to highlight that because that's going to be very important. It wants the center of mass for the composite body of A and B. So now it wants the center of mass if we combine those two shapes to make that, well, let's be honest, it looks like a bullet. And one of the things that we're going to have to take into account is that the cylinder B is heavier than the cylinder A because its density is 2 times the regular density. So coming down here, we're going to have to use our composite shape formula. So I'm going to start by going part B. And we know that for a composite shape, we can say that the center of mass Z bar, and I don't know why they always name them Z bars or X bars, because in the end they kind of mean different things, but you guys all get confused. So for a composite shape, it's going to be the summation of Z squiggle I multiplied by mi, all divided by the summation of mi. So this is for center of mass. But if we look, we're not actually given mass up here. We're not given mass anywhere. We're given the density. But it's nice because what we can do is we know that mass is equal to density multiplied by volume. And we know the density of these shapes and we know the volumes. Excuse me. So we can make a nice table because this formula now becomes this. Z bar is going to be equal to the summation of Z, oops, not bar, but squiggle, I times rho I times VI, all divided by the summation of rho I times VI. So what I'm going to do is I'm just going to make a nice little chart for all these and start taking the summations of all of them, which are kind of really boring, but we can do it. So I'm going to leave this as, we'll go shape, I guess. Shape will be the first one. The second column we'll have as the Z squiggle. The third one, what we'll do is we'll have it as volume. So I'm just trying to think of where to put it, volume. And I'll try to make that look a little bit nicer. Oops, I'm kind of zooming out of the page, sorry guys. Volume. And then the last one I'll have as mass. So we know to get to mass, we're just going to take our volume and multiply it in by the rho that we want. So for a shape, well, we'll have, I don't even know what to call this thing, the bullet. We'll put the bullet. And then the second one we have is the cylinder. And I'll just put in brackets here that this is A and this is shape B, in case you guys start to get a little confused yourselves. So Z squiggle is going to be the distance from the origin to the centroid of the shape. So for shape A, it's actually what we just solved for, and it's going to be equal to, and I'll put this in red, it's going to be this 2/3 times r. And that's why it's important that we get the first part of the question right, because we'll be getting the second part of the question wrong if we don't get part A right. So a Z squiggle is 2/3 times r. And for a cylinder, we know that the Z squiggle is just going to be half of the height. So it's going to be, oh, I guess I have to change colors or else you guys won't see it very well. So it's going to be right in here. And we know that the height of this cylinder is equal to r. So we know that the Z squiggle for the cylinder is going to be r/2. And I'm going to put a line between these so they don't get mixed up, because I guarantee that's what's going to happen if I don't. So like this, and like this, and I'll separate everything so it's hopefully a little bit more clear to you guys. All right, so now the volume of that bullet, well, that's another thing I said we solved for. Excuse me, and that's right here. Is the volume is equal to pi r cubed. And that's why it's very important that we solve for it beforehand, because if we didn't, it'd be a real pain in the butt right now to try and find. We'd have to do another integral. So it's always good to have it on hand. So we got pi times r cubed. And for the second one, a cylinder, well, we know that the volume of a cylinder is equal to pi r squared times the height. Well, we know that pi is going to stay the same. The radius of this cylinder, if we look up, well, the radius is just going to be r. So we're going to have r squared pi, and the radius is r squared. And then the height of the cylinder, if we look up, the height of the cylinder is also equal to r. So we're going to come down here. We're going to say this is equal to r. So funny enough, it's going to have pi r cubed as the volume, which is the same as above. Pi r cubed. So now to get mass, and I'll put this in pink here, to go from volume to mass, remember, we just multiply this by the density. So for the first shape, shape A, it said that it has a density of just rho. So the volume for this one over here is just going to be rho pi r cubed. But the density of the second shape was 2 rho. So the mass for the second shape is going to be 2 rho times pi r cubed. Excuse me. Alright. So now looking down here, we're going to take the summation, because as we can see, and I'll highlight this, the bottom of this formula is the summation of mass, or actually it's probably better up here, the summation of mass. So this is one of the things that we should probably sum, is that last column full of mass. And when we do that, we get 3 rho pi r cubed. So this is one of the things that we're going to need in the formula. But if we look, we still need the top part, which is going to be z squiggle times mass. So I'm going to come down here and I'm going to kind of finish in my table. So I'm going to have shape, and then I'm going to have my z squiggle times mass. So if you guys write smaller than me, you guys will have more room. You guys can do this as one big long table. You guys won't have to come down like this. We're going to have the bullet, which is shape A. We're going to have the cylinder, which is shape B. And I can make a nice line across. Nice line. And we're going to sum it at the end because we're going to need this. So if we're looking at this one, and what we're going to do is we're going to take the z squiggle and multiply it by the mass. What we get is 2 over 3 times rho times pi, and then r to the 4. Now if we do the cylinder, well, we're going to have rho times pi times r to the 4. But here's kind of the one thing that we're going to have to keep in mind too. And I want to say this to the end to see hopefully if you guys notice. And this is very, very important. This is one of the things that also applies to 2D centroids. So you guys are going to really want to pay attention to this. Is, as we said, the z squiggle is the distance from the origin to the centroid. So for the cylinder, it's very easy to tell. It's going to be the h over 2 right here. So this this pink, this is our distance that we want. And we know it's h over 2. However, one thing that we have to keep in mind is this is going down the negative z-axis. It's going below the origin. So what you need to do for this type of question is when we're filling in our z-squiggle, for the cylinder, since it's going below the origin, it's actually negative. And it's going to be the same thing over here. This cylinder is actually going to have a negative z-squiggle m because z-squiggle is negative. So when we sum these together, what we actually get is negative 1/3 rho pi r to the 4. So when we sub these two into our formula to find our center of mass for z, it's going to be at the top negative 1/3 times rho pi r to the 4 divided by the second one, which we got as 3 rho pi r cubed. 3 rho pi r cubed. Excuse me. So when we do this, what we get in the end is it's going to equal to negative r divided by 9. So when we're doing our center of mass, our x bar, y bar, z bar is going to be equal to 0, 0, because again, x and y, they're symmetric. We don't have to worry about them. We know that they're at 0. But the z bar coordinate is negative r divided by 9. And this is our final answer. So we're going to put a nice box around it like this. Perfect. So now we're done part B. So those first two parts are kind of really suck. They're really testing all your skills, composite shapes, continuous bodies, everything. So hopefully part C, well, hopefully that's not too bad. When you look at it, you get a little scared at first because it's a 3D shape. And as the first part of part C, it says, what is the moment of inertia? So as soon as I see moments of inertia in a 3D shape, I really don't like it because the integration is a real pain in the ass. However, it's very important that you guys read the rest of the question. It says of the XZ cross section of cylinder B around the x-axis. So this is important because it tells us two things. The first one is kind of at the end here where it says it wants IX. So that's very, very nice because it tells us exactly what formula we need to use. We need to use IX. And the second part is the XZ cross section. So we're not actually dealing with a 3D shape. We're dealing with a nice square, which is this right here. So what I recommend for this question is to actually just draw this shape in 2D to figure it out a lot easier. So we come down here. And for part C, what I'm going to do is I'm going to draw my axis. So we have the z-axis like this. And then we have the x-axis up here. So this right here is z. This one is x. And our shape is actually just this. And if you guys look, well, this is just a nice rectangle. Nothing too special about this at all. I'll try and square it up a little bit. And its dimensions here, from here to here, is r. And these are all given. And then this right here, from here to here, from both ends to both ends is going to be 2r, because we got r on each side of the axis. And if we look, it wants the moments of inertia about the x-axis. So if you guys remember, for these shapes, we have a nice formula that says Ix, and Ix is, this is exactly what we want, is going to be equal to Ix prime bar plus a times dy squared. This is a formula right on your formula sheet. You guys can go to this. So if we look at this, this is just a rectangle. And for a rectangle, Ix prime bar is equal to base times height cubed divided by 12. Excuse me. And if we substitute everything in, well, we know that the base here is going to be 2r. The height is also just r, and this is going to be cubed divided by 12. The area of a rectangle is just the base, is just the base times height. So we're going to have the area is equal to base times height. So base times height. And the base is 2r. And the height is just going to be r. And finally, the last one that we want is dy. And remember, dy is the distance from the centroid of the shape to the axis that we want. So dy, in this case, we know the centroid of this rectangle is going to be right here. So dy is going to be from the axis to the centroid. Right here, dy. And we can easily see that dy is just going to be r over 2. So dy is equal to r over 2. So all we have to do now is substitute all of this into our formulas. So we get Ix is equal to, and the first part is I bar x prime, which we know is 2r to the 4 over 12. 2r to the 4 divided by 12. And then we plus the area. So the area of this is equal to 2r squared. And we multiply by dy. And we multiply by dy squared. dy is r over 2, and we're going to square it. So if we look at this formula, we now have everything just in terms of r, which is what we want. So if we simplify this a little bit, we get ix is equal to 4 over 6, which is, I guess, 2 over 3. It doesn't really matter what you do. 4 over 6 r to the 4. And that's it. So this question is actually really, really easy if you guys know what you're doing. It just looks really, really scary because it's a 3D question. So we scroll up here. We just want to make sure real quick. Moment of inertia about the x-axis. Perfect. It's in terms of r. We're good to go. So that's how you do this question. Part A, well, that really sucks. Part B also really sucks, but it's not as bad as part A. And then part C, really, really easy. So if you guys see a 3D shape, maybe just try and look for the easy questions, because you guys could have done part C right here without doing any of part A or B. However, part B was kind of interesting because you needed part A to solve for part B. So it was a pretty good question, something you should definitely know. 3D centroids are the absolute worst. Moments of inertia is never too bad because they very rarely go to a 3D case for moments of inertia. I've never seen one, but who knows? They might surprise you this year. So yeah, that's how you guys do this question. I hope you enjoyed it. I hope it helped you guys, and I'll see you guys for the next video. And I'm going to kind of go back. As you guys know, I'm doing these out of order. The next video I'm going to do is the bending and shear moment diagrams for this 2016 final. So hopefully that'll help you guys out too. So thank you guys so much for listening. I'll see you guys in the next video.